Let me start by saying that I've really enjoyed hearing about all your research this weekend. I always find it fun to see what types of problems people are trying to solve, what they're spending their time on, so I appreciate it. So today, I'd like to tell you about the acceleration of AI that we built into NVIDIA GPUs, some of the challenges we had to overcome, how this capability relates to graphics, and my perspective on where it might lead. So there's no denying that AI is starting to transform how we think about graphics, influencing content creation with generative AI, providing new compressed representations like NeRFs, and improving the performance and quality of rendering. But the reality is that AI has already disrupted real-time rendering on consumer GPUs for hundreds of thousands of gamers and for years. Hopefully you had a chance to see Edward's hot 3D talk on Friday. But if you didn't, I'll let you know that DLSS is a software solution that leverages the acceleration of AI in the GPU to achieve super resolution, frame generation, and reconstruction, which is like denoising. And it both improves visual quality and performance simultaneously. So our goal when designing a GPU is to unlock the potential of powerful tools like AI to ensure they can make a big impact. And sometimes that's achieved with dedicated accelerator hardware. So let me tell you a bit about how this hardware capability came about. For context, because not everybody is soaking in GPU architecture every day, let's do a quick refresher. This GPU is a sea of programmable cores, a memory system to keep them fed, a way to schedule work onto them, and a series of dedicated hardware accelerators for things like rasterization, depth and blend, and video encode. And obviously the GPU is optimized for massively parallel processing. This GPU, for example, has 144 programmable processor cores. Zooming in on the processor core, the programmable core, which we call the streaming multiprocessor, or the SM. It consists of hundreds of units of math, some local data storage, a way to access memory, and at the SM level, there are also several dedicated accelerators, including texture sampling and filtering, the RT core, which is our name for our ray tracing, traversal, and intersection hardware, and a Tensor core, which is to accelerate artificial intelligence. And the way these programmable cores are typically used is that you run a program that loads data into the SM, processes on it, and then stores the results, repeat. Simple. So we already have the horsepower of all these programmable cores at our disposal. So there are several considerations we take into account when deciding to build dedicated hardware accelerators. First and foremost, we try to find a good problem to solve, and then we have to solve enough of it. So one way to do that is to implement in hardware the part of a key workload that has annealed, or will benefit the most from annealing, for efficiency reasons, for example. But when we do this, we also want to achieve something like an order of magnitude speed up, because our goal is to make the impractical suddenly feasible, so that when a developer plugs in the GPU and they use this capability, it feels like they have a time machine. The thing they dreamed would be possible someday just works. And the reason I say we have to solve enough of the problem is that sometimes it's necessary to build scaffolding to support the main idea, especially with a speed up of this size. But there are some trade-offs we need to consider when doing this. Typically, when you build dedicated hardware acceleration, you gain efficiency, but you lose flexibility. So to mitigate this trade-off, we try to define an abstraction, often a developer API, that lets the hardware evolve under the hood and provides the possibility for other IHVs to implement their own solution to the same problem, and developers' code doesn't have to change when switching between GPUs or between generations of GPUs. A second thing we do to mitigate this trade-off is to provide a slower but flexible fallback path. Another consideration of the trade-off to think through is that adding dedicated accelerators can drive innovation because we're building a foundation upon which people will build further solutions on top of the new capability. Or it could accidentally stall innovation because if you bake an algorithm into hardware, maybe people aren't going to investigate the algorithm much more. So to mitigate this trade-off, we need to really believe in the tool that we're enabling. Even within the company, right? We need to rally different teams. There's hardware teams, software teams, verification, developer relations. And if we can't get our whole company to rally behind the idea and the feature we want to enable in the product, then how can we possibly rally the entire industry to move a certain direction? And secondly, we believe that performance of these accelerators should scale on future GPUs. If you wait long enough, programmable processors could just do the task. But if people are going to build on this foundation, you want the acceleration experience to be long-lasting. And this is why we have so many accelerators that are attached at the SM level, so that as we increase the number of programmable cores, the accelerators that they can leverage increase as well. So let's look at ray tracing as an example of these principles. Before we built dedicated hardware, ray tracing was done on the GPU and software. And arguably it was already accelerated, right? Because faster than a CPU. But we looked at the workload and realized that large portions of ray tracing software had annealed. Everybody was doing roughly the same thing for a large portion of the workload. But that portion took many thousands of instruction slots per ray. It wasn't particularly efficient. Excuse me. So we took that portion of the workload and we built a dedicated hardware accelerator for it, which we called the RT Core. This involved special purpose hardware for box intersection and triangle intersection, of course, but it also involved acceleration structure traversal and fallback paths to the SM to do programmable operations. With this hardware, we achieved greater than 8x performance improvement versus GPU software ray tracing. And so if we take this example and review our considerations I just went through, we found a problem that was worthwhile to solve, or that we felt was worthwhile to solve. We achieved a big speed up. We solved enough of the problem. We helped build an industry standard API and a programmable fallback. And we believed in it enough to try to move the industry over years and generations of GPUs in this direction. So that's the ray tracing example. What about artificial intelligence? If you're not soaking in the topic of AI every day, like I end up doing these days, it may just be a buzzword to you. So here's one way to consider its usefulness. Artificial intelligence is just a toolbox, right? And it contains a variety of new tools called neural networks. One of the simplest neural networks is a multi-layer perceptron, or MLP. And the idea is that it computes weighted combination of inputs into temporary values, we call a hidden layer, and then you do that again, combine those inputs into another hidden layer, et cetera, until you get to the output. And then the weights for this weighted combination are incrementally adjusted during training against the desired output. And then they're frozen and simply used during inference to perform a task at which the network is now an expert. A more complex example, a convolutional autoencoder, is shown in this cartoon. I have to forgive the cartoons. And it consists of an encoder-decoder pair, where the encoder is iteratively performing convolutions and downsampling to build up a multi-scale representation of the input data. And then the decoder can take that representation and project it back to some other representation, an image, for example. An even more complex neural network is a transformer. And this is arguably the most important neural network in the world right now, because transformers are the basis of every large language model you've heard of, including ChatGPT. Now, there's even more complexity in this neural network structure, but I'm not going to go into positional encoding and mass multi-head attention today. You're welcome. But I do want to point out that it also has an encoder phase on the left and a decoder phase on the right. And one thing that's interesting about this transformer is that the output of the decoder is fed back in as an input to the decoder, shifted, so to allow it to process time series of data. So it can understand and then generate paragraphs of text, for example. So these are just some examples of neural networks in the toolbox. There are many, many, many others. But some really interesting use cases of neural networks include image processing, classification, like what is this an image of? Oh, it's a dog. Segmentation and vision for self-driving cars or robotics, and generative tasks like large language models like ChatGPT, and diffusive image generators like Stable Diffusion, Midjourney, etc. Now, developing solutions with these tools is not quite like traditional software development. In traditional software development, you pick an algorithm, you code it up, implement it, test it, and make sure you got it right, and then you go through a phase of optimization to make it fast enough or small enough or whatever your goal is. But for developing with AI, you follow a similar path, but it's still different. Instead of doing algorithm exploration, you pick a network architecture and you choose a loss function. And Pete, in his keynote yesterday, mentioned that finding the right loss function for a problem is a good place to innovate. It's very much black magic, in my opinion. Instead of coding and testing, you train the neural network, which adjusts the weights. Right? You train the neural network on curated data. This is another problem with AI development, that is a challenge, I should say, with AI development, in that how do you find the curated data? How do you make sure it's good? How do you do the curation? And optimization looks different as well. Typically, it's fine-tuning the network or doing precision quantization so it can be smaller or run faster, exploit sparsity, etc. So developing solutions with these tools it's similar in concept, but they differ in mechanism. But the tools can be quite powerful, and from my perspective, a lot of the power of these tools is that they can leverage learned latent space representations. So recall the autoencoder I mentioned before, where I said that the encoder was doing iterative convolutions and downsampling to build up a multi-scale representation of the input data. That representation is the learned latent space representation I'm referring to. And I think it can be thought of like you've done a coordinate system transform, or you've projected the input data onto an alternate basis set of functions, where computation is less expensive or information can be stored more efficiently. And all the math people have to forgive me for really stretching the envelope here with this. But I think we can look at some non-AI examples as to the power I'm referring to in this concept. JPEG 2000 compression takes this image, does a discrete wavelet transform, and then you compress it by throwing away the lowest energy coefficients in the expansion. Or recall that a convolution in real space is equivalent to a product in Fourier space. So for a large enough convolution that you need to perform, it might be less expensive to do a Fourier transform, then a multiply, and then an inverse Fourier transform, as opposed to doing a direct convolution in real space. The good news is, with AI, we don't have to choose Fourier space to solve our problem, or which wavelet variant is the one for my problem. With AI, this basis set is learned during training. It doesn't have to be an orthogonal basis. It doesn't even have to be complete. It can just be a dictionary of functions that it figured out best represent the data it's been shown. And to demonstrate some of the power of this, this particular network architecture is useful for image processing tasks. So things you can do that leverage this latent space representation, or you could do denoising in that latent space. Or you could perform super resolution by building an asymmetric decoder here. Once you have the latent space representation, the decoder can take that out to whatever resolution you want. So it just builds a bigger, more upscaling on the decoder side. So let's talk about how these tools are then processed on the GPU. Neural networks are typically complex layered graphs of matrix operations. But often the matrices are larger than can fit on a single SM. These aren't 4x4 matrices by any stretch of the imagination. Each layer is therefore processed by parallelizing it across the GPU. And tiles of inputs are loaded by an SM and then processed into outputs. And I've shown this in a cartoon of a single layer of a matrix operation on the right, where the input activations are the rows colored in red, and the input weights are the columns in the purple box colored in red. And the outputs processed by a single SM are the tiles shown on the green outputs. And so other tiles are worked on by other SMs or by the same SM at a later time, for example. So these matrix operations are really the basic building block of neural networks. As shown in this cartoon, there's a phase where there's a matrix multiply accumulate, which is performing a weighted linear combination of inputs, followed by what's called an activation function, where a nonlinear envelope is applied to those temporary values. In the activation function, other processing can happen, like normalization or precision scaling. And the outputs are called output activations, which are then the input activations to the next layer in the network. So we can just compute those matrix operations in the existing SM core. Each thread in a warp is a collection of 32 threads on our architecture, has a private set of registers holding the data and feeds a scalar math pipe. In this case, I've shown an FFMA, which stands for fused floating point multiply accumulate. And a long string of these scalar ops per thread can comprise the matrix math. But we're talking about acceleration, so we really want to achieve acceleration for this building block. And it turns out you can't just drop 10x more math right here and hope for the best. It just can't be fed in the same way the scalar pipes are fed. Some limiters for making that happen are register file bandwidth. The register file is a RAM, and you can't read out of it at 10 times the rate without building something completely different to solve that problem. And instruction issue rate. If we want to do 10 times the math per cycle, we would have to issue instructions 10 times faster. And that's a whole other part of the control section of the SM that would have to be rebuilt for that purpose. So it's pretty invasive, but there are some opportunities we can exploit to make it less of an onerous problem. The first is that for these matrix operations in neural networks, it turns out that if you do it just on the SM in these different lanes, different threads, there's a bunch of redundant data being stored across these threads. And secondly, we can take advantage of the fact that we want to do a matrix operation, but we're using scalar operations here to get it done. We're doing long strings of scalar operations that then build up into vector operations, then build up into matrix operations. So to solve this problem, we implemented operand sharing across all 32 threads. This removes redundant RAM accesses, all the redundant data, to feed a large block of math shown here, which we call the Tensor core. And along with that, we leveraged the fact that we want to do a matrix operation instead of a long string of scalar operations and built special instructions to do just that. So you can see in the table on the upper left that through operand sharing and special instructions, we reduced these bottlenecks for achieving higher throughput and are able to have a higher throughput of math that's effectively fed. So basically, that's the nucleus of the NVIDIA AI hardware acceleration, the Tensor core. It accelerates the basic building block of all neural networks by doing a matrix multiply accumulate, implemented in parallel dot products through a warp synchronous, all the threads work together, collective operation. And it achieves a throughput of at least 8x higher throughput than the standard SM math, depending on the data type you use in the market for the GPU. The Tensor core supports multiple computation shapes, which can help with efficient tiling for data movement, as well as several data types or precision for the numbers. And here I've shown an example of a shape and a set of precisions where the input activations and the weights are represented with 16-bit floating point, and the output activations are represented with 32-bit floating point, just as an example. The thread numbering shown here is just to highlight that the 32 threads within the warp are collectively holding all of the A, B, C, and D operands that are needed to process this result as a whole. So the matrix multiply accumulate is handled by the Tensor core. But it turns out the uniqueness of network architectures is often between the matrix multiplies. I mentioned some of these operations before: normalization, precision quantization, and of course the various nonlinear envelopes that are applied, transcendentals, etc. So we found that processing the activation on the SM programmable core maximizes flexibility, ensuring our hardware is able to cope with whatever is invented next. I'll highlight at this point the transformer network that I showed before that's taken over the world was just invented 6 or 7 years ago. And it now is starting to run everything. So who knows what's going to be invented next? We want to make sure that our GPU is going to be the best for running that, no matter what. Another thing processing the activation on the SM programmable core allows is that we have an affinity between the Tensor core and the SM. And we can exploit this affinity to leverage, for example, shared storage for efficiency reasons. So there's a bunch of other little reasons that this is a good idea. We made a similar decision for ray tracing, where the RT core that I described earlier and the SM can collaborate on ray tracing traversal and intersection as needed. For example, custom primitive intersection shaders. So over time, we've increased the throughput and the capability of the Tensor core. One example is that we enhanced the Tensor core to add support for sparsity. I mentioned before that during training, you set the values of all the weights for the weighted combinations in the network. It turns out that typically dense trained weights are often just 0 or very small values. The good news is that we already know the answer to the question of what happens when you multiply by 0 or add 0, and we can exploit that. So we added an idea called structured fine-grained sparsity, where you can take advantage of the fact that some of these weights are already 0, or you can round down small numbers to 0 explicitly through fine-grained structured pruning, such that you only allow 2 out of every 4 elements in this weight matrix to be non-zero. That's why it's structured and fine-grained. So doing the pruning and then fine-tuning the weights that remain, the non-zero values that remain, to ensure that you don't lose capability from the network that you trained. You're not throwing away its goodness by rounding down numbers. The fine-tuning of the weights can be done to make sure that the structured sparsity can be exploited. And so then we just compress away all the 0 values and just store and process on the non-zero data and carry around some metadata for the non-zero indices. Where were those values in the original matrix? Those indices are used to mux in the appropriate input activations, so we're not multiplying by values we shouldn't. And that's used to compute the output activation more efficiently. So because we're using structured sparsity to ensure that exactly half the values remain, we get a 2x speed up. You get 2x the Tensor core throughput and a 2x reduction in the weights footprint and bandwidth at approximately no loss in inference accuracy through this trick of fine-tuning the weights as you prune. As we've increased the Tensor core throughput, not just through sparsity, but just brute force, efficient data movement becomes critical to keep the Tensor core fed. So on the left, I've shown the memory hierarchy for getting data from the DRAM all the way to the Tensor core on our GPU. We have an operation run from the SM called load global, which goes and fetches data from DRAM. It passes that data through the entire memory hierarchy, through the L2, L1 cache, and into the register file. And then we do a store shared, which can take the register file, the data you've loaded in the register file, and it stages it into a shared memory, which is a scratch pad. Because you want to use the data multiple times, you want to stage it there. And then as it's needed, it's pulled from the shared memory scratch pad into the RF register file, which then feeds the Tensor core. The problem with this is that we end up using the level 1 cache and the register file more than we need to, right? We're reserving space for the return data while it's loading. And the in-flight data could be hundreds of cycles. So that's a waste of storage. So what we did is we implemented a fused load from global memory with stores to shared memory scratchpad to avoid this temporary staging in the register file storage. Now in this case, we're reserving the scratchpad room for the in-flight data, but that turns out to be much less of an egregious problem. Also fusing this into an asynchronous copy here, we've turned what was 3 reads and a write across these various RAMs into just 2 reads. So it's more efficient. And there are many more examples like this. This is sort of like building the scaffolding around the main idea that I mentioned earlier. But this is one good example that was added a generation after we put the Tensor core into the GPU. So we've increased the throughput over time. And this plot shows that we've increased our single chip inference performance for data center GPUs by 1,000 times over 10 years. Now, we didn't add 1,000 times the math hardware. We made the GPU 1,000x, rounding a bit, more efficient. And that was done through building the tensor cores that I just described, as well as exploiting several things listed on the left. Number representations using lower precision data. We're able to process faster, move without running into bandwidth limits. The special instructions I mentioned. The manufacturing process, but that turns out to be one of the smallest pieces. So moving through manufacturing process over time, one might naturally think, well, that's where the efficiency is coming year after year. And it's through these other things that are actually much bigger. Number representation is a 16x enhancement, for example. And we also added sparsity that I just described a couple slides ago. Alongside this efficiency improvement, series of efficiency improvements, the model efficiency, the neural networks and how they're used is also improved. So the overall gain is actually greater than 1,000x in data centers. And 1,000x and a lot more coming was necessary and continues to be necessary because AI data centers are tackling absolutely huge problems like generative AI. Some of the chatbots we may have used are running on tens of thousands of GPUs at the same time. Not necessarily doing 10,000 problems at once, but working together on a single problem. And it's only going to get bigger. Well, it turns out that generative AI can be used to create graphics assets. So tying this back into graphics, I have an example here of a tool called Edify, which runs in the cloud, and it's a generative AI tool. And it can do nifty things like turn a sketch, simple sketch, into an image with a guided prompt to help create the image you want. So here the image looks somewhat like your sketch, but it looks a lot better. Another thing you can do is take a static image or just a photograph and turn it into a tileable, physically based material, including all of the properties like normal maps, etc. And the third example I put here is to take a single static 2D image and automatically turn it into a 3D model, maybe for rapid prototyping. So the speed of the data center can be a boon for tasks like this. Generative AI can also collaborate with other software tools dynamically to serve content for interactive avatars. So with this example, NVIDIA's Avatar Cloud Engine, or ACE, a gamer could theoretically speak to a game through their microphone, And then we use speech recognition to turn that into text, send that to a large language model to interpret the text, to generate dialogue for this particular character in the game, which then goes through another layer of text-to-speech. And then the speech audio can be fed to a tool called audio to face, which performs animation of the avatar's face to match the words that they're saying that were just generated by an LLM in the cloud. It's pretty wild. To me, it's pretty wild. It's exciting that people are figuring out ways to use the power of the AI, even in the data center, for interactive experiences beyond text-based chatbots and search. But even on a consumer GPU, recall the example of DLSS from earlier, which leverages the tensor cores I described to achieve both an image quality and performance improvement simultaneously. It's also very exciting in a different way. And whether in a data center or in a consumer GPU, the AI acceleration that I described is being leveraged to achieve these enhancements. Oops. So there's another thing I'd like to highlight. We built both the RT core dedicated accelerator for ray tracing and the tensor core for artificial intelligence acceleration at the same time. They were released in the same GPU. And they've continued to evolve together over generations of GPUs. These dedicated hardware accelerators, plus a ton of software, like RTX and DLSS, they've proved to have an impact greater than the sum of the parts, in my opinion. So it's really great that we put them in at the same time and they got to evolve together and work together to solve problems. The impact that I'm seeing them have is that they've really brought in the practicality of real-time path tracing by years versus waiting for generations of GPUs. Some examples are shown here, Cyberpunk 2077 and Portal RTX, another good example, Alan Wake 2. And bringing in this capability by years, it's what I was describing before, it's a time machine. We made this possible that wouldn't have been if we hadn't made these investments and made them work together. So next, I'd like to share my perspective on where we might look next for AI graphics impact. And in particular, I'm talking about on consumer-level GPUs rather than in the data center. I think that AI could also make an impact on rendering tasks other than post-processing like DLSS is. And so what this means is we have to try to use AI to solve thread scale problems rather than GPU scale problems. This implies that the AI we use will need to use very small neural networks by design for performance reasons. So let's take a look at some recent research that attempts to use AI in this manner and see if we can derive an emerging trend. The first example is neural texture compression, which uses a small multi-layer perceptron to decompress stacks of material properties. There's one MLP network per material texture stack. The MLP only has 2 hidden layers, and they achieve a 4 to 16x compression improvement over standard block compressed textures. So you can have higher resolution textures in the same memory footprint, or you can have equivalent resolution in a much smaller memory footprint. The next example is real-time neural appearance models. These are small MLPs that represent the layered material parameters, and also they also approximate the scattering math for the material. So in this case, there are 2 MLP networks, one for BRDF evaluation, one for importance sampling, per material, and they have to be trained per material. Each of these MLPs only have 2 to 3 hidden layers, so they're fairly small. And they've achieved a 2 to 4x performance improvement. I think it's actually higher now, but this is what the paper says. So if you're still around this week, go see the talk. And so I think this is a really interesting step towards getting real-time performance for complex, multi-layered, really film quality materials. This example has layers of dust and fingerprints and scratches, all sorts of things on it. Really impressive stuff, and very exciting. A third example is neural VDB, which uses a neural network to represent both the compressed volume data as well as a sparse tree topology that allows you to look up the data very quickly. So this uses 2 to 4 MLP networks per volume, Each of those MLPs has 3 to 4 hidden layers, and they achieve a 10 to 100x compression ratio for their volume data. Again, if you're here later this week, go see their talk. My final example is the neural radiance cache. This uses a neural network to encode sampled radiance information. So it's a little bit like a neural light probe. And you can see in the center of the image that adding the neural radiance caches to the path tracing improves the sample quality dramatically, which can make your image converge faster or make denoising easier. The neural radiance cache uses 1 MLP network per probe. The network only has 2 hidden layers. And the radiance probes, interestingly, the radiance probes are updated, meaning they're incrementally retrained, and queried, meaning they're just asked what an answer is, that's inference, dynamically. And this allows it to handle moving light sources, dynamic scenes. And so it's really interesting, it's doing online training this way. Well, I'm betting you can guess what the emerging trend is here that I wanted to talk about. It's that these simple multi-layer perceptrons are surprisingly powerful. They're really good for data compression. They're good for approximation of complex math. And they're good at caching of complex signal data. Because they're small, performance can be competitive with traditional rendering, which makes it very exciting. People can start using these. Especially if you take advantage of some tricks for performance and performance efficiency, like layer fusion and leveraging reduced precision and sparsity. Very exciting, but there are some challenges to overcome. If every thread in the SM, or in the GPU, is running its own neural network, it's querying a neural network for its own texel value, then we have to overcome divergence because the threads are meant to work together. So there's both execution divergence, which I just described, but also data divergence. You have to load all the weights for all these networks, and every thread needs a different set of data. And we also need to figure out how are these network inference operations going to intermix with traditional shader code, because maybe the network won't completely replace the shader, maybe it just is a task within a shader. And as an aside, I'd like to point out that even some of these MLP examples are leveraging the encoder-decoder pairs I mentioned before and learn latent space representations. Neural texture compression has an offline compression phase, and it's compressing into a latent space representation. So then the MLP you run at inference to query for a texel and all of its components is taking as input a much smaller texture of latent vector values. And those are fed into the network, and your texel values and all of your material parameters for that texel pop out. So it's that same power, but it's just being used, broken up into 2 pieces with encoding and decoding. But whenever I chat with somebody about AI making an impact on graphics, eventually they end up asking, will AI just render the whole image? It's a good question, and I don't know the answer, but I can try to highlight some of the obvious open questions that do need to be answered before we can answer the big question. Imagine you want an AI to do this. What will be the source of your high-quality training data, your curated data that you're going to use to train this to do the right thing? And if it's doing such a big task, how are we going to make it stable, temporally stable even in its output, reproducible, interactive so you could control it, real time so you can tolerate looking at it? And we have to ask this question also about how will it interact with traditional rendering? Will traditional rendering compute a simple version of the image you want? Will it have to compute some of the difficult lighting in the situation in order for the AI to get it all right? I don't know, but I think it's an area really ripe for some great innovation. There's a lot of opportunity here to learn things that nobody knows the answers to these questions. And I think that there are some There are some exciting advancements in techniques like video diffusion models that might help us think through the problem, but probably aren't strictly the answer to this problem. So here's a still from an OpenAI video created with Sora. And it's a video diffusion model that is generating the whole image. So let me hit the animation here. When I saw this, you should read the technical report, it's fascinating, but they don't give a lot of details. When I saw this, I said, this could be a game. Like, the AI is rendering all of this. It has an implicit understanding of all the physics involved in order to generate the dust clouds, in order to make the shocks of the truck look good. Let me play it again. This was generated from a text prompt and nothing else. The text prompt was something like a truck driving down a windy mountain road that's dusty or something along those lines. But I look at this and it's generating all this foliage, and it's mind-boggling to me. But this thing probably took tens of thousands of GPUs to train, and the inference for this probably needs to be 3-4 orders of magnitude faster in order for something like this to be practical for interactive rendering. So maybe it's not the solution. It's probably not the solution. Clearly, I'm torn over this. But I think there are lots of open questions. It's exciting advancements to see stuff like this happen, and there are a bunch of competitors just coming out now for Sora. And I'm going to keep an eye on this, and I think others should as well, but there are lots and lots of open questions. So, in my opinion, AI graphics is the future. Maybe not exactly what that last slide showed. But it's clear to me that AI is going to end up disrupting all industries, all fields of study. We've already seen examples just in this talk of content creation and complexity impact, of render performance and quality impact. The good news is we already built AI acceleration into NVIDIA GPUs. So we built the time machine. And the question you can ask yourself is, how can you use these sets of tools to transport the future to now? What new neural network models will you invent? What new applications will you find for them? And how will we take feedback from those and build new GPU enhancements, which then may enable the next generation of new network models? This virtuous cycle of innovation is underway, and I heartily encourage you to jump in and make an impact. Thank you.
Okay, thank you very much, John. Very inspiring talk.
Thank you.
So we have time for questions. Does anybody want to start?
Any thoughts or insights into the divergence question you mentioned, the threat divergence for graphic shading? Do you feel SER is enough there, or do other things need to change?
I think SER, which stands for shader execution reordering, if you don't know about it, is a way of extracting coherence so that things can run sort of in parallel, simply. Just to give context, sorry. I think SER is part of the solution. I think we'll have to go further than that, and we have some ideas, but it's not quite yet a solved problem. Yeah. Yeah, sure. Yes?
Maybe also on the same divergence question, more in the concept of spanning MOPs, different for each thread. And you build Tensor units with big matrices.
That's right.
But they all want different things.
That's right.
They all want to do different things. How do we see the solution to that problem?
Yeah, so this is exactly the problem, right? So one way is to use SER so that each of the threads are hopefully, you've extracted enough coherence in execution that each of the threads is actually running the same MLP. Because lots of pixels in a pixel shader are actually doing the same thing with slightly different inputs. So you might load a unique input for a thread, but all the threads in a warp, or a collection of threads, that then feed the tensor core are all running the same neural network, the same weights, but they have different inputs, their own unique inputs.
Maybe I'm asking, like, in terms of, like you said, with every shader, you mix machine learning with traditional shading. So we're not talking about ray tracing. You say, I'm putting an LP in the shader. Each
Yeah.
How do I take advantage of tensor units? Because they're not designed to use that.
Oh, I see. You're saying because SCR isn't enabled for non-ray tracing shaders?
General,
Yeah.
your idea of MLPs, small MLPs per thread mixed with shaders.
Right. I think the only way to do that is through something like SCR. We'll have to figure out if it can be extended to other shader types, compute or pixels, because it's a fundamental problem. How do you gather together enough of the work that you can use the tensor cores and get the throughput? Otherwise, you're going to be serializing through all the different things, and you don't get the advantage of the throughput. Yeah. A bunch of questions over here. Go ahead.
While NVIDIA is still dominant on AI acceleration for some in the GPU side, so actually there's so many startups of building some own small NPU or some other big tech build their own silicon. So what kind of the NVIDIA's perspective, those kind of trends?
So I didn't catch all of that. What kind of perspective? What perspective on what?
So those kind of the a lot of the potential competitor, maybe
potential
some competitor, like building some dedicated small scale dedicated NPU hardware or something like that. So those kind of company, NVIDIA's strategy or something.
Are you talking about in other GPUs, or are you talking about
MPU? Yeah, so it's dedicated hardware. Yeah.
Yeah, not dedicated hardware embedded in GPU, just general dedicated
small,
hardware
not,
just
not,
for this
not
problem.
dedicated hardware inside the GPU, only the dedicated hardware.
Yeah. The problem, I mean, this is my personal perspective, but the problem I see with dedicated hardware that isn't tied to a GPU is that you lose that entire ecosystem that you can use to do all the things around the neural networks that you're using, right? And that's why we prefer having it pretty tightly coupled, so that you can do programmable code on an SM, and then go to the tensor core, then go back as often as you need to for your particular problem. And so somebody could go out and build their own dedicated hardware that just ran convolutional autoencoders, right? But how are you going to do all the other stuff you need to do?
So NVIDIA does not feel any kind of threat.
We feel threats from everywhere. Only the paranoid survive. It's so true, and we behave that way. Like, there's lots of smart people everywhere, right? We don't have that hubris. So I think that some people, some niches will find. Sorry, let me say the sentence again. Some competitors that are deep diving into particular very dedicated solutions for really hard problems that are important, they're going to have their own space. They're going to have their own niche. But if you need it to be programmable, if you need CUDA in your data center, and you need that programmability, it's our intent to make sure that that's the best experience you can get is on our GPUs. Does that make sense? Yep. Okay.
Case for me and you.
I've got a question related to that philosophical idea of when do you be programmable versus when do you commit to a particular format. You had an insightful slide on when and how do you build dedicated hardware. And you pointed out that when you when you commit to a hardware solution, you might be accelerating innovation and you might be foreclosing innovation.
Mm-hmm, right.
And you prefer to keep the hardware details hidden behind an API so that the hardware can evolve separately from the problem space. Right. One counterexample of that came to mind was texture compression, mm-hmm. where the format is exposed publicly and agreed on industry-wide. Right. And maybe this is an example of where innovation has been foreclosed. And I'm wondering, what would your philosophy be? How would you apply these observations to the innovation shown later on of structured sparsity? Mm. And forgive me, I don't know that technology well. I don't know whether that's done in the driver. Or are you applying loss to the user's matrix? Or does the user apply that loss by rounding things down to zero? And what do you foresee in terms of APIs, et cetera, for handling sparsity and so on?
Okay. Lots of good questions embedded in that. So Yes, it's true that texture compression became sort of baked, and the dedicated hardware maybe means that people aren't spending so much time coming up with new things. But the neural texture compression, I think, is an example that completely elides the texture unit. It's, you're looking up individual texels. There's no filtering involved. You have to do stochastic filtering. And someone could implement 16-tap texture in software if they wanted to. There is a programmable fallback. You don't have to use that hardware, but it's a lot slower. So it becomes just a trade-off. If it's more important for you to have 64-tap in ISO, you can go get that done with the program instead of using the hardware. And it's going to run slower, but that might be not as important to a user, depending on their problem. For the fine-grained sparsity, the typical case for using that is that the user would need to be aware of it. And because you have to do, or it's probably likely that you have to do the fine-tuning to update the non-zero weights to make sure that you don't lose the expert level of your network that you trained when you started pruning. So I don't think it's necessarily something the driver would do under the hood. Now, maybe something like that could exist. Maybe it already exists and I'm just not aware of it. Someone could opt into that and say, I'm willing for you to make it lossy. As long as it's close to what I trained, I'm fine. But if it runs twice as fast, that's all I care about. There might be cases for that, and for all I know, we already have software that does that. I don't know. I don't know how to answer the part about whether there's an ABI to be built or an API. Maybe. Lots of people work through libraries that are provided by the vendors, right, including NVIDIA. And if there's an abstraction to be found there for fine-grained sparsity, I'm sure we'll look at it and figure out whether there's something that actually allows innovation or alternate implementation, or whether it's too specific to actually abstract away. Yeah. Did I answer all of them?
Perfect.
Okay, good.
There was one more question. Oh, here.
So the RT core and the Tensor core are fascinating, super effective, will continue to co-evolve in fascinating ways. I wonder if you'd like to go out on a limb and predict what the next disruptive accelerator might be on the future.
Wow, haven't we done enough? Let me think about that.
We won't hold you to it.
You know, I actually thought, I don't know, upset some of my colleagues in the room. Okay, I don't want to talk about any future product or anything, but until I saw the neural appearance models, the sort of like neural materials, until I saw that research start to form and work, I spent a lot of time thinking about how to accelerate materials. Like, was there an amazing Uber material, Arnold shader or something that could, take some complex thing with 50 inputs and build some dedicated hardware that just blasts through it, or samples multi-layer with Monte Carlo or something, position-free Monte Carlo or something. And it led basically nowhere. But I think there's not an obvious next disruption that's going to come from dedicated hardware that I can see. I think the next disruption is going to be about, and why I gave this talk, is going to be about using the tools we've just enabled to take that next step without needing hardware, because the hardware is already accelerating the building blocks from which we could build something new and exciting. And I think the neural appearance models thing is a good example of that. We already built the hardware. We just didn't know that it was good for that until we tried. Does that help? Okay.
There was someone.
What are the prospects for having the GPU issue in building GPU autonomy, things like work graphs, as opposed to relying on the CPU to issue the work to the GPU?
Yeah, I think it's pretty common to be CPU limited when using a powerful GPU, and that's a shame. I think word graphs are going to be good for getting around that problem. But I think that's just the very first step. right? I think work graphs are going to be powerful as well to do more complex work management on the GPU itself. Making the GPU self-sufficient is sort of the first step that work graphs is trying to help get over that activation energy, right? But once we get over that, then I think it's sort of unexplored territory. So I think there could be some exciting stuff there. Things we might not ever afford to do in a driver, you could do on the GPU. And some things it just won't make sense for. So we'll have to see, I think, how it works out. So I don't really have anything really concrete to add there other than just hope. Yeah.
Yes, please. Yours.
What are the trade-offs that go into managing the silicon area for SS? You're adding all these dedicated accelerators. You could add more scalar units, or you could go them all the way and just add a gigantic tensor core. And that's sort of some balance between betting on the future versus supporting backwards compatibility.
Yeah.
How do you make that trade-off? Is it market-based currency? Is there some element of hopefulness involved in that?
Well, I think it came down to a few things. One that I mentioned before is that if we're going to add an accelerator, it better really accelerate. Like, you better get something like 8, 10x, something like that, maybe more if you can. If you can't get that much, if it's going to be 10%, why bother? Just, convince somebody to increase the clocks on the GPU and it'll go 10% faster. Put a better cooler on the thing or something, overclock it, you're done. So that's one thing. It had to be big enough to be exciting, in other words, right? But when we first came out with the Tensor Core, I got asked, I think it was SIGGRAPH 2018. After that, and I was meeting people, and somebody asked me, so how much area did you spend on that? And I said, just enough to be exciting, right? It's actually less than you'd think. It's probably much less than you'd think. And something similar for the tensor cores. It was giving a big enough speed up. It costs what it costs. And so if we want that speed up, that's what we do. And sometimes we have to. Our CEO is sort of known for saying that NVIDIA goes after $0 businesses and then creates huge business out of it. And so there's a little bit of leaning forward into the future that we try to do when we're making these decisions about what to try to enable and make exciting next, where there are no workloads that we could use practically that would show us the value of adding these things. We have to use some vision and make some convincing arguments internal to the company, et cetera. It's not straightforward because there is risk and there's cost. Simply adding more programmable cores would have gotten us a few percent more performance. That wasn't what we were looking for. We're looking for 10x. Any other questions?
Okay, I think we are on time.
Okay.
So let's thank again, Ron. Thank you very much.
Thank you.